By the late 1990s, the transition to 64-bit computing required the microprocessor industry to push fabrication into entirely new physical realms. Intel and Hewlett-Packard committed $5 billion to a project named Itanium, built on a strange engineering paradox. To create the most powerful processor in history, they decided the internal hardware needed to become significantly simpler. The entire architecture was designed around one metric: instruction-level parallelism, or ILP. ILP is a measure of how many separate machine instructions a CPU can execute at the exact same time, within a single clock cycle. The dominant 32-bit x86 architecture was physically running out of room to extract this parallelism. Managing the chaotic flow of instructions required adding increasingly complex logic gates to the chip, eating up power and space. Extracting more speed out of silicon meant the microscopic geometry and logic processing of the die itself had to be completely rebuilt from the ground up. Zooming into the microscopic topography of a CPU, the pursuit of parallelism splits into two distinct competing philosophies. The first is out-of-order superscalar execution. The second is explicitly parallel instruction computing, or EPIC. Superscalar execution uses heavy onboard hardware to analyze incoming code, constantly hunting for instructions it can execute simultaneously as the program runs. EPIC strips that hardware away. It demands that a software compiler find the parallelism and organize the instructions perfectly before they ever physically reach the chip. This was a multi-billion-dollar bet on where the physical limits of semiconductor manufacturing lay. Intel wagered that offloading complexity to software would yield performance gains that hardware could no longer achieve on its own. Visualize these architectures as two industrial models. Superscalar is a reactive robot swarm. The hardware dynamically grabs instructions, determines dependencies, and reorders them. This requires massive silicon real estate dedicated strictly to sorting data. In contrast, EPIC operates as a pre-planned assembly line. By removing the sorting hardware entirely, EPIC shifts the burden of organization to the software compiler. The compiler acts as an omniscient manager. It analyzes the code, predicts the branching logic, and aggressively organizes the instructions prior to execution. These pre-sorted operations are packaged together into massive 128-bit blocks known as instruction bundles. An EPIC template explicitly tells the CPU hardware exactly which parallel lanes each bundle should be fired through. The hardware does no thinking, it executes. In theory, this is pristine logic flow. You get vastly simpler hardware, reduced thermal load, and maximum throughput per clock cycle. But an assembly line requires perfect conditions. Etching this theoretical blueprint into physical silicon introduces chaotic microscopic variables that no compiler can predict. The first fracture in the EPIC design appeared when engineers tried to map the blueprint onto a physical silicon die. To make the Itanium viable for enterprise servers, engineers had to add massive L3 memory caches alongside hardware dedicated to legacy x86 compatibility. These required architectural additions caused the transistor count to bloat exponentially. In 1998, Intel planned to fabricate the chip using a 250-nanometer photolithography node. That specific laser etching process had a hard maximum reticle limit, an absolute boundary on how wide a single chip could be. The bloated transistor count triggered the Muffin Top Crisis. The Itanium's physical layout expanded beyond the area the 250-nanometer tools could print in one pass. You cannot fabricate a processor that spills over the laser's exposure limits. The geometry is impossible. The software-driven dream was immediately halted by the uncompromising physical boundaries of fabrication tools. To save the design, management ordered a desperate engineering pivot to the 180-nanometer process. The tighter 180-nanometer mesh successfully contained the bleeding blueprint. The chip now fit onto a single die. Packing millions of transistors into a smaller area meant a massive increase in thermal output and highly condensed routing complexity. Adding to the friction, Intel aggressively targeted an 800 MHz clock rate for the initial launch. At 800 MHz, electrons must cross specific distances on the die with incredibly tight fractions of a nanosecond to keep the system synchronized. The dense routing created a critical bottleneck. Signals arriving at different logic modules were consistently out of sync, simply because the physical distance between modules was too great for the clock speed to tolerate. This exposed the fatal vulnerability of the rigid epic logic. Moving one logic block to fix a timing delay altered the geometry of the entire layout, immediately creating new distance delays in downstream modules. Engineers were trapped in a cascading debugging loop, endlessly chasing signal timing errors across the silicon. An architecture built on theoretically perfect timing becomes unsustainable when subjected to the physical friction, heat, and distance delays of actual silicon. Looking back at the two industrial models, the 180 nanometer failures clarify exactly why the assembly line broke down. While Itanium stalled under brittle timing constraints, Intel's 32-bit Pentium Pro utilized its robot swarm to dynamically route around these exact types of physical delays in real time. The epic gamble failed because it assumed a software compiler could accurately predict the microscopic, real-time physical state of the hardware. The relentless march of Moore's law ultimately punished the compiler and rewarded hardware logic. As transistors continued to shrink, the complex scheduling hardware required for out-of-order execution, which Itanium sought to avoid, became incredibly cheap to manufacture. Software compilers, no matter how advanced, remain completely blind to runtime variables like sudden cache misses or microscopic thermal throttling. The adaptable x86 hardware swarm eventually absorbed 64-bit memory extensions natively, achieving Itanium's goal while keeping the resilience of dynamic execution intact. Itanium did not fail due to a lack of engineering ambition. It failed because in semiconductor manufacturing, brute force physical adaptability will always outlast the rigid perfection of software theory.